Before anything else, I owe you guys an apology. And you may sense the nature of the apology when you see that something's changed with me. Now I'm wearing my mask. And to be entirely honest, the reason why I wasn't following the rules before is because I figured I've had COVID and so I'm special. Well, I'm not special. It doesn't matter that I've had COVID. I need to follow the rules. And I was entirely in the wrong. Worse yet, worse to me, I don't know if others would agree with me on this. Worse than that, if any of you interacted with me on the matter at all, I think you will find that all I did was complain and whine and vent. And it was childish and selfish and unprofessional. And I've no excuse for my behavior. So I apologize. It won't happen again. It stops now. I hope you can find it in your hearts to forgive me. More to the point of what we're doing in class. I have to stop there first. My department head clarified the rules for me the other day because I hadn't really bothered to clarify that for reasons previously stated. But they are as follows. When I'm lecturing, I must either wear a mask or wear a face shield and stand behind the plexiglass window. Both of their pluses and minuses. I feel like slowly but surely I'm getting better at speaking clearly underneath the mask. I'm gonna order some face shields also. When I get home, I'm gonna buy some off of Amazon. Much to my surprise, they're very reasonably priced and made in the US, and there's lots of them in stock and all that. So I was very happy to find that out. Realistically, I'm not gonna have them Friday. I might not have them Monday, but we'll try that out too. We'll see if it's any better. My concern is I want you guys to be able to hear me. You know, we have to make the best of what we got. That really, I've made tons of mistakes over the past few days. I wish to God I were the sort of person who always did everything right and never made mistakes, but that's not reality. So when I do screw up, I try to admit it and make it right. Another mistake I made is I realize now that I was completely blinded to just how stressed everyone is. We're all on edge. Students, faculty, administrators, all the way up and down every level. Everyone is on edge, including me. And I just didn't realize it. So hopefully my eyes are a little more open now, but I give you my word, I will not cause any trouble in those two areas. Leaves open that I might cause trouble in other areas, doesn't it? But I give you my word that I will not cause you any trouble in those two areas. I will follow the rules and I will stop being a whiny little fill in the blank with whatever word you like. Yes? No, I verify, I've confirmed that. Those are my two options. It's either a mask all the time or a face shield and, not or, and the plexiglass window. I confirmed that with my department head. So we'll try both. When I get the face shields in, we'll try them. I'm a little concerned because if there's anyone who's particularly hard of hearing, you just lost the ability to read my lips. Oh, you see, so the face shield might work out better in them. In the meantime, I hear tell that the closed captioning in YouTube is really not bad, certainly better than in Zoom. So there's that at least, but we'll try all the above. You know, we'll just see what works the best. Okay, so with that unpleasantness out of the way, let's see. So we ended up last time, I believe, talking about resonance. And I said resonance is a tricky topic. It's one that I have to keep on my toes with till this day, and I've been thinking about these things for 25 plus years. Just to remind myself that resonance is not an equilibrium. There's nothing flipping back and forth. You will notice that in your book, this is where they introduce arrow notation, curved arrow notation. That's something we're going to use a little bit this term. Resonance is the very worst place to use it. because curved arrows are used to show the movement of electrons, because that's what chemistry is. That's what a chemical reaction is. It's electrons moving from between these two atoms to these two atoms, or something, and repeat several times. That's what a chemical reaction is. And of course, as we just got through saying the other day, with resonance, there's no electrons moving. So it's really kind of bogus, and it's always kind of irritated me. They do the very same thing in the Chem 227, 228 book, by the way. They do it in pretty much every organic textbook I've seen over the last 10 to 15 years. And in fairness, I get why they're doing it. What they're trying to do is to provide you guys with a tool that you can use to help yourself find other resonance forms if you're given one resonance form. See what I mean? And you can use it that way. You might find it doesn't particularly help you to use it for that, and I certainly don't want to force you. But that's what you can use it for. Ultimately, we will be using curved arrows a little bit to describe organic reaction mechanisms. We do so very, very heavily, of course, in 227 and 228. We don't have time to do that quite as much here. So I would certainly say read that part of the book, and maybe be prepared to put it to use later on, a little bit at least. But just remember, arrow pushing and resonance really is an oxymoron, because you're showing electrons moving that aren't really moving. So I think probably you see what I'm ranting about this by this point. So, use caution. Just with that cautionary note out there, I think we're fine. Why do I have a red box all of a sudden? All right, who did that in chat? No, it seems I did it. Good, I think that's all I really need to say about that. Interestingly, and I don't know why you care, but at this point in 227, we've turned right and gone into acids and bases. We're going to get there eventually. We're going to cover some other topics about structure and nomenclature, and today, functional groups before we get there. So we're going to go the other way, and that's fine. It'll all come around eventually the same way. What I want to talk about mainly today, and we will do a reef session later, again, just to try that out. It looks like it's working. The only thing I do have to give you a bit of warning about with the reef polling is it's not absolutely instantaneous in terms of grading. It may very well say you have a 0 or 3 out of 10 or something completely wrong like that. That's because I need to get in later on and tell it how to grade it. So that'll get fixed eventually, but it's not instantaneous. So hopefully we can work out most of any issues with reef sooner rather than later. So far it seems to work pretty well. Yes, at the end, I'm going to be dropping at least the lowest 30% of your reef grades, but clearly we all want to get it to be working as well as we can get it. So we'll give that a try later. What? Oh, interesting. Huh, okay, someone in chat did do that. I can probably turn that off if need be, but no drawing funny pictures in the meantime. Okay, so where I want to take us next is different ways, and there's more than one way, of categorizing or classifying organic compounds. And as I said, there's more than one way to do that. This is important. Anything you can do to break down the members of a field by categorizing or classifying them only helps you study that field. Like I think that's fairly self-evident, right? That look at the biologists. They have all these different ways of classifying organisms. What, kingdom, phylum, class? Do I still remember this from like 100 years ago? Kingdom, phylum, class, order, family, genus, species. Isn't that crazy? I remember that, but not the quadratic formula. Be that as it may, I think I've made my point. Anything you can do to categorize members of a group helps you study the way all those groups in a certain field interact. And it's the same with organic molecules. The first way is to make a very simple division, and I think it's one worth mentioning, which is the difference between those compounds which contain at least one ring, as it's called, and those compounds that don't. And we'll call the compounds that don't contain any rings in them And by a ring, I mean that the chain is bent around and then connects again. There we go. I can handle it. And that's a thing that can happen. And we'll get to that in a moment. And we call compounds like that cyclic. If there are no such rings like that in the compound, then we call that compound acyclic. And really, you can break down the term cyclic further into carbocyclic compounds, and these terms are in your book and in the class notes. Carbocyclic compounds where the ring, the atoms in the ring are all carbons, and what we call heterocycles or heterocyclic compounds. We're terribly prejudiced as organic chemists. We just love carbon so much that it's basically carbon and everything else. So you got the carbocycles where the ring is completely carbon and all those other things over there because they contain, you know, horrendous heteroatoms. They're not carbon or hydrogen. Okay, so I just off the top of my head have put a few acyclic compounds here, trying to give you guys a mix of line angle drawings and condensed structures. But these are all examples of acyclic compounds. There's no rings anywhere. The chains can be branched or straight, but there are no rings in any of these compounds. And we'll learn how to categorize these before long too. We'll learn that this first one is an alkane. Over here we've got an ether. Actually that's MTBE, methyl tert-butyl ether. It used to be a gasoline additive to increase the octane rating. It's unpocotoxic and not the greatest thing in the world for the environment, so they switched largely to ethanol. So that's ethanol. That of course is the intoxicating component of adult libations. They're talking about AL2 in chat, so I think you got my email. I don't think there's now anything due on Friday that's graded. I think the intro assignments still are due on Friday, though what does that mean if it's due if they're not graded? Probably nothing much. I do recommend you take a look at that. Certainly do get started on the other ones, but like I said, yesterday I just suddenly had this new perspective of just how stressed out we all are. And I thought, you know, maybe at the beginning of the term at least, it won't hurt me to be a little bit more flexible. So nothing is due that's graded until a week from Friday, which I guess is September 4th. So do take a look at the intro assignments. I've had some people asking me questions like, how do I answer this type of question? How do I put in superscripts? How do I do this? It's all, at least in principle, answered in the intro assignment. So do take a look, but it's not for grading. Okay, so those are acyclic compounds. So as for the due dates, and they're asking what other things have been moved, well, the due dates are given on AL. So whatever it says now, those are the due dates. So that might make chapters 1 and 2 due next week, which I think will be done with chapter 2 by then. So I think we'll be in good shape. I think allegedly we're finishing chapter 1 today. Good, so all of these are acyclic compounds. There's no rings of any kind in any of them. Well, what do we mean by a ring? Well, I think if you think about it for a moment, in order to have a ring, you need at least 3 atoms, right? 2 of anything can't form a ring. You just get a line segment in between them. So you need at least 3 atoms. And perhaps the simplest carbocyclic compound is this one here with 3 carbons. Pretty soon we'll learn that's called cyclopropane. Benzene, which I think we've talked about a little bit, is a cyclic compound. That's also a carbocyclic compound. It's C6H6, and the 6 carbons are connected into a ring. Over here, we've got a 5-membered ring with 1 CH3 coming off. We'll soon learn that's called a methyl group. And that's still a cyclic compound. It doesn't have to be only a ring. There can be other things sticking off. There could be other atoms. You could have chlorines or OHs or what have you. And it would still be a cyclic compound. Seeing as in this and in this and in this one and also in this 4th one, all of the atoms directly involved in the ring are carbons. Seeing as that's the case, I would say all 4 of these are carbocyclic. Even though there are heteroatoms, there you go, heteroatoms over here, that oxygen is not included in the atoms that make up the ring, right? It's sticking out off the ring. So I would say these four are carbocyclic if you wanted to categorize it further. But you can have heteroatoms, most often oxygen or nitrogen, included in the ring. This compound happens to be called pyridine. I don't know if I really care if you know that it's called that. I hope you never have to use it. It smells just awful. Unfortunately, it's not infrequently used as an industrial solvent, but nasty stuff. It's basically just like benzene, except you've replaced one of the CHs with a nitrogen. And so that would be an example of a heterocyclic compound. This is also a heterocyclic compound. We've got a 5-membered ring with 4 carbons and an oxygen. And then I just have this CH2OH group sticking off. That doesn't make it not cyclic. It can still have other atoms sticking out from the ring. That's perfectly allowed. But that would also be an example of a heterocyclic compound. And so rings have to be at least, there's no such thing as a 2-membered ring. You have to have at least a 3-membered ring. How large can the ring get? Arbitrarily large. There are, I know of pharmaceutical compounds. I think these are largely antiviral and anti-tumor agents. There's one that I'm pretty sure has a 14-membered ring. So they can get pretty big. I would say the ones you're most likely to run into most often are 5- and 6-membered rings. Those are quite common. We'll learn why. There's a reason for that. But any ring of any size, with or without heteroatoms contained in the ring, is going to be a cyclic compound. If all of the atoms in the ring are carbons, and by in the ring I mean directly involved in the ring, the ones that are directly bonded to make the ring, then you have a carbocyclic compound. But if you've got a heteroatom included amongst one or more carbons, then you've got yourself a heterocycle. So cyclic compounds can be either carbocyclic or heterocyclic. I don't wish to confuse you guys with this. It's just in case you run into these words so that you know what they're talking about. But all of these fall under the umbrella of cyclic compounds and all of those under acyclic compounds. My whole point to this, the reason we're talking about this, is we're learning how to categorize compounds. So this is one way. This is a very simple division between cyclic and acyclic compounds. Question, how can you tell what these things are? Is it because you've been doing it for so long? Well, I don't know what all of these are. I don't think I could tell you too much about this compound. Pretty soon, by the end of class today, you'll be able to tell me it's got an alkene functional group and that it's got an alcohol functional group. And I suppose if I tried really hard, I could name it. But I don't really know much about it beyond other alcohols and other alkenes that I've used. Others of these compounds will turn out to be ones that I know something about, but certainly not all of them. Please don't be too impressed. Okay, any other questions then so far? Yes? Right, we covered polarity briefly. Certainly, I would not expect you guys to, we didn't even really so much briefly, but you covered in Gen Chem. I would certainly never expect you to do anything with dipole moments with numbers. You know, what is the dipole moment of this compound in Debye units? No, I would never do that to you. But the way you know if a compound is polar or not is as follows. First, you need to figure out what the polarity is of all the bonds in the molecule. And you know how to do that with electronegativities. And again, I don't think you need to memorize electronegativity values. We did go over the general trends, though, in electronegativity, I believe. So that can help you make some decisions that way. And so that's the first thing you have to do. And you also need to draw the molecule in its correct three-dimensional geometry. Again, I'm hoping they covered this in Gen Chem. I always did, but you never know what you get anymore these days. So once you do that, you need to look at all of the individual bond polarities and decide whether they cancel out or not. So did we do CCl4? I feel like we did. So here's an example of a molecule with an sp3 hybridized carbon. And so that means it's tetrahedral at the carbon atom, and that's what I'm trying to show here. It doesn't have to look exactly like this. There are other correct ways to draw a tetrahedron. I might have put the two straight lines over here and the wedge and the dot on this side. It's fine, it's the same thing. All you've done is turned it a little. However, I was very naughty and forgot my lone pairs. Shame on me. For shame, for shame. Okay, so I think you'll agree all four of these bonds are polarized towards the chlorine, because chlorine's more electronegative than carbon. And again, I don't care if you memorize the number, but I would expect you to be able to tell looking at a periodic table, chlorine's more electronegative than carbon. So it's like they're all pulling electrons in that direction. But all of those cancel out. And the way you know that is as follows, since I see someone asking it. The way you know whether they cancel out or not is you play the, well, there's two ways I can answer that. The first level, the first way I can answer that is, it unfortunately involves math. I don't know if you've done any vector geometry. You add up all the vectors and see if they cancel or not, or if there's a non-zero resultant. That may help a few of you. If you've not had vector geometry, don't worry. You don't need to know that in order to understand that. Here's how you know whether they cancel out or not. We're going to pretend that the center of the molecule, this carbon atom, oh, I don't know, you can put a box there or whatever. You can just say that whatever these atoms are, the peripheral atoms, they're all pulling on that carbon atom. And since all of these atoms are the same, they all have the same electronegativity, they all pull with exactly the same strength. And as a result, these two will result in pulling this way, those two will result in pulling the exact opposite way, and they will cancel out. That's one way you can know. Another way you can know is by building a model. If you can beg, borrow, or steal a molecular modeling kit, that might help you to see it. But it does take some practice. Now, what would an example look like where you can know that it wouldn't cancel out? Well, easily done. What if I did that? Now they no longer cancel out, right? Because we have one bond that's different. What section does this pertain to? I don't know I could try to look it up later, but it should be in chapter 1. It's going to be where, it's going to be amongst the things you learned from Gen Chem. I better just get it now. This refers to section starting around section 1.5 or so, where it starts talking about polarity. And again, it's part of the Gen Chem curriculum. Now, that doesn't mean that I don't care about you guys, right? I care about all my students. If you're struggling with molecular or bond polarity and you want to bring that to office hours, please don't hesitate. That's what I'm here for. So I'm glad to help anyone out. I just don't want to spend a great deal of class time since it was in Gen Chem. But it's that earlier part of the chapter that this is referring to. Good. I think that's about all as far as that goes. Now we can, you do not need to retake Gen, at least I hope not. Good. Well, you know, those of you who are struggling with this, please don't hesitate. I'm happy to help you. I'll gladly help review these things in office hours. Or if you're working in problems and want some help working them out, or here's what I tried on this problem, am I doing it right, am I on the right track? Please don't hesitate. Email and office hours are both fine. Good. So much for acyclic and cyclic compounds. Let's lose all of that. A much more, how shall I say, detailed yeah, that'll work, much more detailed way of categorizing organic molecules is by something called functional group. And I've defined functional groups in the class notes. The definition, I shouldn't read to you, but the definition of a functional group is a piece of a molecule. So that's first. A functional group is a piece of a molecule, certain atoms that are bonded together. And that piece of the molecule, always without exception, is bonded together just that way. And what functional groups do for us is they enable us to tell what a molecule is going to do, because we can see what the pieces of the molecule, what the functional groups are that are present. And we're going to learn about, maybe not every single last one of them, but how most of these functional groups behave. The reason you need to know that is because you're going to be working with compounds that contain various different functional groups. And it would be good to have some idea of what to expect when you're dealing with them, because they aren't all created equal. Oops. Let's see. Let's see. I've also put in boldface in your class notes what it means to know a functional group. And I don't know that I've got a 100% perfect exhaustive description there, but what I put here is knowing a functional group means that you can recognize it wherever it may show up, no matter which direction it points, even if it's in a molecule you've never seen before. So I'll also let you know this, there's certainly a big list of functional groups in your book. I'm not going to go over them one by one, maybe from a slightly different perspective just now. That's what we're going to spend most of the rest of the class on. What was I going to say? But I would not recommend that you flat out memorize that whole table. That is not the same thing as knowing functional groups, because you can memorize every last little bit, but not be able to apply it. And I want you guys to be able to apply it. So that's where we're going to go next. Let's see. Let me go back to my pen drawing tool. First of all, let's cover the compounds that consist only of hydrogen and carbon. We call these hydrocarbons. That's sort of a general class. And I would say there's 4 flavors of hydrocarbons, not really getting yet into functional groups so far. There's a lot of words to learn in this class, I admit it. But I'll try my best to get us through that. So those 4 classes of hydrocarbons, let me just, hydrocarbons. I'm sad to say it looks better when I draw it with the mouse than when I use a stylus. That really makes me sad. So the 4 classes of hydrocarbons are alkanes, A-L-K-A-N-E-S. And we're going to get to them first, I think, in the grand scheme of things. Then you've got alkenes. So we change this A to an E. And, oops. And then alkynes. And by the way, every single one of these I defined in the class notes. So all the definitions are in there. And last of all, you've got aromatics, or aromatic compounds, also called arenes. Oops. Aromatics, or aromatic compounds. So those, I would say, are the 4 classes of hydrocarbons. These 3, I would say, fall under the definition of functional groups that you find in your class notes. Those count as functional groups. Why am I leaving off alkanes? And it's something that I've had a lot of discussions with students. I don't know that it's really that critical. The main thing I'm wanting to avoid is that if you see a molecule with 5 functional groups over here, and there's a little piece of it over here that's just an alkane, we don't go after that and say that the molecule is an alkane, right? Alkane really almost can be defined as a molecule that has no functional groups. It's just hydrogen and carbon and single bonds, and that's it. There's no oxygens, no nitrogens, no multiple bonds, no nothing. That's the way, to me, the term alkane implies really an absence of functional groups. It's okay if that doesn't make perfect sense right now. The other 3, though, I think you'll see that there's a difference between them and alkanes. We've already seen a bunch of alkanes. The simplest alkane would be methane, CH4. Doesn't get any simpler than that. That's the smallest possible alkane. You have to have at least 1 carbon. And pretty soon we'll learn how to name them up to about C10. You might have heard of methane and ethane and propane and butane. Those are pretty commonly used. The good news is after that it becomes regular. It takes the Greek prefixes, pentane, hexane, heptane, octane, and so on. So we'll get to that pretty soon. But those are the simplest alkanes. Alkanes can be branched. I think I drew one for you on my previous screen. That would also be an alkane. And I think you'll agree with me, there's nothing remarkable here at all. There's no multiple bonds, no heteroatoms. It's just carbon and hydrogen in single bonds. And so that would count as an alkane. What about cycloalkanes? Well, they're a thing. Oops. Certainly they exist. That would be an example of a cycloalkane. Now you'll notice this is not benzene. I haven't drawn any double bonds, right? It's all single bonds. So cycloalkanes really are a kind of alkane too. They're very similar. And the reason we make these distinctions is because it tells us something about what these molecules do. And I think we'll get to alkanes pretty soon in the next chapter or two. What do alkanes do? Not a whole lot. They're pretty unreactive. The main thing they do is burn, right? They're quite flammable. They will react with oxygen, but not very much else. Once we start adding on other atoms and even putting in multiple bonds, we'll eventually get to all this. You don't have to know it all right now. But once you start mixing this up, once you start adding other atoms or adding multiple bonds, that's when these molecules begin to take on certain characteristic reactivities. And that's what we mean by functional groups. They help us to remember how a molecule is going to behave given what groups of atoms are in it. So alkanes, there's not that much to say on, though we will talk about how to name them and what their properties are in an upcoming chapter. Alkenes and alkynes, on the other hand, add on something to alkenes. So for alkenes, if you look at the definition, you'll see that we need at least one carbon-carbon double bond. And I've put that in the class notes. I only say that so I don't have to write double bond, at least, that I don't have to write it down on the whiteboard here. But I've put all those definitions in the class notes. So the simplest possible alkene, I can say, so alkanes can have rings, sure. Alkenes can have rings. That's supposed to be a bond, by the way. That looks absolutely awful. So the simplest possible alkene would be C2H4. You can't have an alkene with just one carbon because you have to have a carbon-carbon double bond. Can't form a double bond to itself. So that's the smallest possible alkene. Happens to be called ethylene. It's the monomer of polyethylene. And how many things do we make of polyethylene? Goodness. Everything from plastic bags to plastic wrap to soda bottles to the bottle caps themselves are made of polyethylene. I would not be shocked if this bottle is polyethylene. So it's used by the ton every day. But you can have a bigger molecule. You could have, I don't know, 5 or 6 carbons, and maybe there's a double bond over there. That would be an alkene. And the idea with alkynes is very similar, except that instead of having at least one double bond, you have at least one triple bond between carbons. And so the simplest alkyne would be this molecule, C2H2. Happens to be called acetylene. I don't really care right now if you know what these things are called, but you might have heard of acetylene. It's used in welding pipes. Acetylene torches burn with an exceedingly hot flame, and so you can weld with it. But again, one could imagine a larger compound, a bigger chain with a triple bond in there. This also brings up someone, well, at this point, there's always someone real sharp. Probably a lot of you are sharp in this way and wondering this question, which is, what if there's both a double bond and a triple bond? Can a molecule have more than one functional group? Absolutely it can. That happens quite a bit. So if you see a molecule with a double bond and a triple bond, both in different places, of course, what do you put down in the exam? What do you say it's called? Is that an alkene or an alkyne? Yes, it's both. You can't separate one from the other. It is both of them at the same time. You could have something that's an alkene and an alcohol at the same time, or an ether and a carboxylic acid. Happens all the time. Look up any pharmaceutical drug molecule. Tons of different functional groups. So it's very common. And you might have to pick out each one of them individually, or you know, any number of different ways that can be put. But it's very, very common for a molecule to have multiple functional groups. Okay, aromatics. Well, for us, I'm going to say that aromatic compounds are benzene and derivatives of benzene. So benzene is C6H6, or if you want to draw it with the circle inside, I don't care, I often do. Or any derivative of benzene. If you replace any or all of the hydrogens with something else, you've still got yourself an aromatic compound. What do you want? Maybe an ethyl group over here, maybe an OH group over here. So this compound would be an aromatic compound and also an alcohol. We're going to define that functional group shortly as well. We have till 3:45. Just want to make sure. So, so much for the functional groups that consist of hydrocarbon portions. After that, we start to add other atoms. And that's when the chemistry gets interesting. And that's when we get into other types of functional groups. So I'm not quite sure how far we'll get through this. I would sure like to take care of alcohols and ethers. Where's my amines? Amines are over there. And then maybe begin to get into the carbonyl containing groups. And if we have to leave the rest for Friday, that's fine. I think we'll be okay. So far, so good. Any questions so far? What this means in terms of what you'll need to know in terms of your learning is I would expect that you could look at a compound, even if one you've never seen before. But you can go, aha, there's a carbon-carbon double bond over here. Even though I've never seen this before, this is an alkene. See what I mean? That's the kind of thing. That's what it means to know a functional group, not memorizing a table. And I wouldn't recommend that. I don't think it's a good use of your time. Good. So, you know what? I almost want to leave the carbonyl containing groups for one chunk. So what do you say we do this? Let's talk about alcohols and ethers, since there are some similarities there. I also want to mention amines. I might go a little bit out of order. I think it'll make a little more sense. And maybe what about alkyl halides or haloalkanes? Right. That makes sense, because those all involve single bonds. And then we'll worry about all the carbonyl guys maybe on Friday. Good. So, oh no, what is the extra line? Oh, okay, he's got it. Good, okay. So let's do alcohols. I have some pet peeves in terms of spelling, although I'm never going to have the opportunity to grade you on your spelling. It's still a pet peeve of mine. I have like 3 pet peeves. This is one of them. There is only one H in alcohol, please and thank you. It is not alcohol. A-L-C-O-H-O-L. And you can define an alcohol a number of ways. Often they use this R group to define compounds. And the R is used kind of like an unknown, kind of like X in algebra. It means it can stand in for any kind of carbon group. And what we find is that R can in fact be any kind of hydrocarbon group. The one thing R cannot be is what's called a carbonyl group, C double bond O. Because as we'll learn next time, once you put that in there, you no longer have an alcohol, you have a carboxylic acid. And they have somewhat different properties. So the simplest possible alcohol, I would say, is methanol, CH3OH. Right, you just replace one of the hydrogens of methane with an OH group. And then you can't get a simpler alcohol than this. Right, if you take the carbon away, you've got water. Water is not organic. So that's the simplest possible alcohol. I already mentioned the next one, CH3CH2OH, that's ethanol. That's a 3, though you'd never know it. That's the next larger alcohol. Whoops. And you could keep going, propanol. You might be familiar with something they call rubbing alcohol that you can buy in the supermarket or drugstore. That is isopropyl alcohol. So I'll draw it with a line angle drawing. Well, I kind of crunked up that one bond. Let me fix that. So there's a carbon over here, and that carbon is attached to two CH3s, two methyls, one hydrogen that's not shown, and the OH. We call that 2-propanol or isopropanol. That's rubbing alcohol. You can buy that in the store. What, I'm sorry? Yeah, these two things coming off are CH3s, because I see only one bond coming away. So there must be 3 bonds that are not shown that are to hydrogen. Yep. So all of those are alcohols, and you can have an arbitrarily long chain with an OH group on it, or some chains and some rings with OHs on them. All of those would be alcohols. So the alcohol functional group, what's different about denatured alcohol? Interesting question. Denatured alcohol is one way that they offer ethanol for industrial use. And denatured alcohol means that it has been made undrinkable for obvious reasons, so that people don't drink it. And they do that by adding a little bit of, sometimes of methanol. Methanol is stupidly toxic. I guess ethanol is a little bit toxic, if you wanted to be technical about it. Methanol is ridiculously toxic. Back in the days of Prohibition, they were making alcoholic beverages in their backyards with stills, and they would get some methanol in there with the ethanol, and people would drink it and die. So it was pretty bad. So they add just a little bit of that, and also sometimes other things like ethyl acetate. Yeah, they're defined by their R group. Yes, that's the one thing we cannot have for R, any kind of C double bond O. That is a big no-no for alcohols. But I think pretty much any other kind of carbon group would work fine. Next time we'll learn that if you put a carbonyl group on, you no longer have an alcohol. You've got carboxylic acid. And they're somewhat different. It's a different functional group. What about ethers? Ethers are in some ways like alcohols. Ethers are kind of what you get when you condense 2 alcohols. And we'll actually learn about this later. It's an old way of making ethers. I would define an ether as R1OR2. Where both R1 and R2, they can be the same or different. They can be pretty much anything other than carbonyls. And the other thing they cannot be is hydrogens. Because if you think for a minute, what if R1 or R2 is a hydrogen? Well, then you've got an alcohol, right? So that's why. They need to both be hydrocarbon groups. So the simplest possible ether would have 2 methyl groups over here. People are adding their artwork. Thank you. I love the go get it spirit. But so the smallest possible ether has 2 methyl groups here. That happens to be called dimethyl ether. It's not really used much. You might have heard of something just colloquially called ether. That turns out to be diethyl ether. And that was used for a long time as an anesthetic. It's a rather pleasant smelling molecule. And if you smell enough of it, you will eventually get drowsy and fall asleep. So that's what they mean by ether. We had an example of another ether on the previous page. Ethers can be cyclic. You can incorporate the oxygen into a ring. Generally, it'll be either a 5-membered ring or a 6-membered ring. That's certainly what those are supposed to all be, just electron dots. Goodness gracious. I think, they're all, it's 2 lone pairs, right? Because it's an oxygen. So that would count as an ether also, just happens to be cyclic. Let's see, so much for the oxygen ones. I want to also talk briefly about alkyl halides, which are just what they sound like. I probably hardly need to mention. All you need to do to get an alkyl halide is take a hydrocarbon and replace at least one of the hydrogens with a halogen, fluorine, chlorine, bromine, iodine, any one of those. So, the simplest possible alkyl halide might be like chloromethane. CH3Cl. But again, you could have an arbitrarily large compound with arbitrarily ugly rings and chains on it. And if we drop in a couple of bromines or a couple of chlorines, then we've got ourselves an alkyl halide also. So the rest of the molecule can be as large as you need it to be. As long as you've replaced at least one hydrogen with a halogen, any halogen, you've got yourself an alkyl halide. Pretty straightforward. These things don't get too much use except as precursors to things. I'm just trying to give you some background that might be interesting here for you guys. One thing that's really peculiar, and I can't really explain it, it seems to me that the more hydrogens you replace with halogens, the less flammable the compound gets. And I couldn't really tell you why. A lot of the materials that are used as fire extinguishers are heavily halogenated compounds. What are the requirements for an alkyl halide? Well, you just take any hydrocarbon, we've defined hydrocarbons, and replace at least one hydrogen with a halogen, any halogen, fluorine, chlorine, bromine, or iodine. You do that and you have an alkyl halide. So it's a hydrocarbon with at least one hydrogen replaced with a halogen. And you can do multiple ones too, like this one. So there's really not too much to that functional group. It's pretty much what it sounds like, alkyl halide. Wait, have we done reef yet? Nope, I'm saving it for the last 2 minutes. And it might be that I don't have time to ask the questions, in which case I'll take attendance. I have no intention of being unfair here. I really would still like to cover amines. So it might be that all I do is take attendance. If I do that, then probably what I'll do is I'll take the reef questions I would have asked and still put them on eCampus because they'll have the answers and you can use them to practice. So last but not least, amines. Amines are organic derivatives of nitrogen. And I'll be honest, I'm not usually happy with how they define it in organic textbooks. I like to define amines as follows. I like to say that it's a nitrogen that has at least one R group on it. It could have more. These other two bonds can be either to hydrogens or to other carbons, but you do need at least one hydrocarbon group for it to be an amine, right? Because if you don't have that, then you've got NH3. NH3 is ammonia. That's not organic. So amines are organic derivatives of ammonia. The simplest possible amine would be methylamine. And again, I don't care if you know what it's called right now. But these things do have names. You can't get a smaller amine than this one. But you know, you can have 2 or 3 groups attached. You got a propyl group and a methyl group. And what the heck, a benzene ring. Sure, why not? Why not? I just feel like putting a benzene ring here. That would also be an amine. All you need to get an amine is take ammonia and replace at least one of the hydrogens with a hydrocarbon group. You can do more than one, but there has to be at least one. So these are examples of amines.